Clayton Spinner here. This is my submission for the ATTiny project with interrupts. This video is just going to go through the code. Basically what I used is, you see these here, these were given to us by John in a post on the forums on Blackboard. Basically he gave us the pseudocode to help us get started with the interrupt writing. So I left those in because they're pretty organized. Sometimes I moved the code. Sometimes I just left his comments here, as you can see. Sometimes I interspliced them with the actual code that we ended up using. So let me start at the top. Basically, at the very top, you have the include file, of course. Here are all the definitions for the registers we're going to be using, giving them names. Many of them are the same. I still have the same convert variables that I used before for the BCD conversion. But using interrupts, after this point, it gets a little different. Basically, you start here where the encode segment for the program, set starting memory, define each interrupt vector. So this is the interrupt vector table. There are, I believe, 19 in all. Looks like 12 is 12, 13, 14, 15, 16, 17, 18. Yeah, 19 in all. Each of them have a different function, a different place where an interrupt can be coming from, from an external from an external source to the CPU. So number 12 is interrupt, pin interrupt. Basically, it's an interrupt coming from either pin B or pin D. And that's what we're going to be using because we have the temperature sensor connected on pin B. And that's what we're going to check for. Whenever that happens, an interrupt will occur, and we have a direct jump to label pin. So what the interrupt does is it breaks out of the main program code and runs this code before returning to the main program loop. So the first time through, this is where main starts. You run this code, you hit the program loop, which sleeps, so it's just waiting. It's not doing anything else. If you're using interrupts, you can have a CPU just be doing calculations constantly, or you can have it here just sleeping. But basically, whenever an interrupt happens, it will break out of whatever it's doing, go to the next step, or at least save the next instruction to come back to, and then run the interrupt routine, whatever you've defined that as, and then it will jump back down to the main program loop once it finishes the interrupt routine. So let's say we've got a change on pin B, interrupt number 12. It's going to jump to pin, which executes this code. First, it saves the values in the status register. These are things like 0, carry bit. You want to save this status register because this status could be, or this status register could be holding values that are being used by the CPU and that are being calculated, and you've just interrupted them, so you got to save it because your interrupt may have its own flags that are set, and you don't want to overwrite those flags with from the ones that are from memory with ones from the interrupt. So you store the status bit, you disable the external clock because you're going to grab its value and put it into X. And basically you just dump it right into X, and then reset the clock back to 0 to start counting again. And you do that through here. And then you put the status back into the status register. And then RETI is return into the program from wherever you came from. And that returns it back down here. Now, so that's the interrupt routine that happens every time there's a pin interrupt. And basically it just dumps the value into X and then goes back into the main program. Dumps the value from the external clock, from the timer. So the main program basically does our setup that we had the simplified version of the setup that we had from the non-interrupt version. You set the stack pointer for the stack. You set the stack pointer for the stack at the end of memory. That's what RAM end is. Set that to the mask. Give the mask to the stack pointer low. These initialized ports are the same as before. We're basically setting up the ports to be used for the output with the LEDs. Now here we're doing a couple different things. These are setups to be able to use interrupts. First you enable sleep mode because we're going to be sleeping in our main program. So you want that to be enabled. And basically what we're doing, this command right here, it looks like a logical shift, but it's just SE, which is predefined as a certain spot within the 8-bit mask, is set to 1, and then that mask is given to this register. And so the bit that controls whether or not sleep is enabled is in the 6th place, so that it sets that to 1 and then gives the mask to the register, to the relevant register. This is the pin change interrupt. It basically allows for, if there is a pin change, to trigger an interrupt. It sets which pin will be the interrupt, pin 3. That's where our temperature sensor is attached to. And then we set the prescaler too. We're enabling prescaler 8. This divides the timer or the external clock by 8 before it's given to the program. And it provides smaller numbers so that way we aren't calculating the full value of the external clock, which are potentially very large numbers. It gives us it divided by 8. Lose a certain degree of accuracy with that, very small, but it makes the calculations a lot more manageable. So then you clear the status register from any flags you'd set, and SEI is enable global interrupts, or just enable interrupts. So now they're running. Turn it on. We had interrupts off before because while we're setting this all up, we don't want to have an interrupt that messes up our entire setup and possibly get stuck in an infinite loop. So speaking of infinite loops, this is loop. It will just run forever. First thing it does is it goes to sleep, and it just waits until there's an interrupt. The only thing that will kick this out of sleep is an interrupt. So once we get an external interrupt, it will jump to pin because we've enabled the pin interrupt, and it will start executing this code, which I've already gone through. Basically just dumps the clock into the X register and returns back. It also resets the clock to 0 as well. So then here is where it gets interesting. Basically we do one of two things depending on what pin 3 had changed to. Now the interrupt triggers regardless of what pin 3 becomes. Just if it changes at all, the interrupt goes. But we care about, for our program, whether or not it changed from a 0 to a 1 so we can know what we've been counting. So SBIS is skip if bit in IO register is set, meaning if the third bit in pin B is set to 1, go ahead and skip the next line, which is recall count ones. If it's set, this is the one does the opposite. Skip if bit in IO register cleared. So if it's 0, go ahead and skip recall zeros. So because you have both of these here, whenever a loop gets interrupted, it's going to do one of these. Whichever one it does just depends on what the pin is. So if the pin is set to 0. So if the pin is just changed to 0, you go to the count ones routine. And you do that because if it had just changed to 0, it means that it was 1s before. And that clock that you had running that you just reset again and dumped into X, that clock was counting the number of X's you had. The number of 1s that you had. So now what you want to do is you jump to count 1s, and we're just going to count them up in a fashion similar to before, where we multiply each one by 25. This while one loop, basically it just subtracts 1 from X which is again the counter or the timer number. Every time we do that, multiply or add 25 to y, which will result in the timer times 25 being stored in y at the end. And then ret just returns to whatever called it, which is the program loop here. So what we've done is whenever the pin changes to 0, means we just counted our ones, and count ones multiplies them by 25 and just leaves it in the Y register for now. It goes down here, skips over this, and goes back to sleep. Basically, it returns to loop and then goes back to sleep. So now the next time an interrupt occurs, which is when the temperature sensor will change again, it'll go up, it'll do pin again, dump the new value of the clock into X, and then this time it'll jump over SBIS pin B3, and it'll hit this one, recall zeros, because we just counted the zeros. So now we're going to jump down to 0, and this is where the heavy lifting goes. Basically, this program is from here on is actually the same as the calculations we did for the first program. Again, this part of the code written by Professor Rosine to do some of the preliminary calculations. He divides by 4 the value of the timer, sets up TMPC as 235, and here figures out the number of times that X goes into Z, where in this case X is the zeros, and subtracts that from 235. Number of times X, which is the zeros, goes into Z, which is the ones. That makes more sense. Subtracts that from 235, and that's basically the equation 235 minus X divided by Y, or ones divided by zeros. And then here it's the same conversion to BCD that we had before, basically the exact same. So the only difference down here is this ret at the end. Whereas before we'd have a jump to the top of the program, and then we'd wait for the zeros to start coming to count again. We have a return, which returns to the main loop here, and basically it just goes back to sleep again. Sleeps until, and then the whole process starts over again. It waits till it gets an interrupt. It will count the ones, goes back to sleep. Waits till it gets an interrupt. Count the zeros, go process them, display them, go back to sleep. So in effect, most of the time the CPU isn't running. It's just sleeping, because every 10 milliseconds it'll count the ones, and for anywhere from 12 to, depending on how hot you get, 20 milliseconds, it will count the zeros. During that entire time, the CPU is just asleep, sleeping, not using power, not running cycles, not doing anything. So this is much more efficient in terms of energy usage. In terms of accuracy, it's better as well, because before we were counting 1 every 47 clock cycles, I believe, and we were using numbers in the hundreds to calculate the number, or calculate the temperature. But here we're using the clock timer prescaled to 8, so it's divided by 8, just to make it a little bit smaller. And the timer is, if it's going at 1 megahertz a second, once every microsecond, you have, what is that, 10,000 divided by 8? So you have on the order of 1,500 to 2,000 samples. So it's a lot more accurate than the original program is. Now in the next video, I'm basically going to go through for both programs our method of testing to determine if the temperatures that were coming up were within the range of what the actual temperature was and within acceptable rates of error. So that's what I'm going to get into now.